We are the Gujarat Technological University. Since its inception over a decade ago, GTU has been empowering young and curating minds to realize their true potential. Over 4 lakh inspired students are enrolled with one of the premier academic universities in India. With more than 450 affiliated colleges in its fold operating across 5 zones of the state, GTU, the International Innovative University, your place to move forward.
Hello and welcome to the lecture on optical amplifiers taken in the subject of optical communication by Electronics and Communication Engineering Department of GANDHINAGAR Institute of Technology. Today in this lecture we'll be studying a very brief overview of various optical amplifiers used in our fiber optical communication system. First off, we'll be seeing here the various applications of optical amplifiers. One of the most common one that you can have is optical transmitter, transmitting the light signal through optical fiber cables, and you have an inline amplifier, and at the receiving end you have an optical receiver. A very simple system and pretty much commonly used everywhere. But if you have the inline amplifier along with an optical receiver present over there side by side, that can be termed as a preamplifier. Opposed to that, we have a power booster amplifier, wherein optical transmitter and an amplifier that we have are placed together. So the output of the optical transmitter directly goes to the inline amplifier, which is like very adjacent to it, right? As compared to your inline amplifier model, where your inline amplifier is kind of equidistant or far away from the transmitter and the receiver both. Right over here you can see we have named it as long fiber link because we have amplified the signal at the transmission point itself to be quite high, as you can see from the height of the pulses over here as compared to the height of the pulses over here. Right, another way is optical transmitter, you have your inline amplifier and then you have a coupler, right, and which from there you are distributing or dividing the light frequencies to wherever you need. As you can see, this does not amplify much, but that is the use of an amplifier itself, because the original signal is of this height approximately, which gets attenuated to a certain extent when it's transmitting, and the amplifier boosts it back up to its original level, and then when it goes to the star coupler, it is then further divided, and during that division process it gets attenuated a bit, so that such that each receiver station needs a little bit of a power boost or an amplifier within itself. A generic optical amplifier consists of this kind of a diagram that you see over here. You have an optical input signal coming in, you have fiber to amplifier couplers or simple just couplers which let you pass the optical signal to the amplification medium in a proper manner and to remove from it in a proper manner also, so that you have very minimum power loss, very high efficiency also along with it. So here you have an active medium. Being an active medium, it requires external source of powers for it to operate. Right, as you can see, your input signal comes in, there is an active medium which gets its power from the source. Power comes in, the active medium then thus amplifies the signal, and then you have your amplified signal as the output, which is then further passed on down the optical fiber cable as and when needed. Amplifier gain versus power, as you can see, in this simple and very easy to understand graph, your gain decreases over as you kind of keep on increasing the power and so on. The ideal point that you'll have is output saturation point, that over here is pretty much the 3 dB point. That this graph does coincide with your digital communication graph of your 3 dB gain, or be it your audio systems, be it your any other electronic systems where you have a lot of gain going through. One of the most commonly used material is erbium. In erbium fiber amplifiers, what you can see over here, this is the characteristics diagram of your rare earth metal known as erbium, right? This is its ground state. Here you can have 980 nanometer photons. This is in the wavelength of 980 microns coming in from the outside, which then induces various transition at various different frequencies. That is at 100, either 1400 nanometers or 1550 nanometers, and these are like what in nanometers, as you can say, are your what microwaves beyond that, right? So 980 nanometers waves you're coming in, and it induces, the word over here is induces, because as you can see over here, it's spontaneous transmission or a stimulated transmission. It might not happen naturally, but it might be even forced also. So you have waves coming in and the light coming in at 990 nanometers, and the output that you're getting is at 1550 nanometers, but the output is further amplified in energy. Various EDFA configurations is you have signal input, you have a tap which from where you can measure what is the quality of the signal that is coming in. You have your optical isolator as mentioned over here in the legend below, right? And a wavelength selective coupler where you are putting in your actual optical signal that you want to amplify, and a pump laser which is your active signal, the signal which will help you pump up or amplify the things. Then you have your erbium doped fiber amplifier, that is your EDFA, erbium doped fiber amplifiers. Then again you have your optical isolators from which you will just select the signal frequency of the signal that you want to transmit, which will obviously be your input signal, which is then further amplified, and you have a tap again to check whether your signals are going properly or not, whether the process has happened or not. And this tap in most of the cases would be linked with this tap as in a form of active feedback. Can be, cannot be, depending on where these taps are taken in, right? And there thus you have your output signal. Similar thing, you have input signal, you have your optical isolators, you have your EDFA present already over here, and then you have your pumps, and then you have your wavelength selective coupler. You have multiple signals over here, out of which you want just only one signal out over here. So this module or this configuration acts like your coupler that we saw over here, or also known as a splitter. Here, star coupler that we talked about, it takes one input wavelength and splits out different wavelengths. So that is where your EDFA comes into picture. This is your wavelength selective coupler. It not only couples, it can also decouple, right? The similar things, you have one input signal coming in over here, you have your wavelength selective coupler present over here, you have your multiple frequencies going in through the EDFA, everything is amplified, sent over larger distances, and at the other end you reach destination of your signal 1, you want it to be separated out. Now you use another wavelength selective coupler, and that's it, you split that signal out and you send it out. That's it. A gain versus EDFA length, the larger the EDFA that you have, the higher the gain you can have, but it reaches a peak value at a certain point, and beyond that peak value it is not a gain, it starts decreasing. Gain versus pump level, and this pump level talks about, the pump level is talking about the active signal that you're putting in your WSC or erbium doped amplifier. Now output versus wavelength, and these are the standard graphs that you can like simply just see and observe. I'll just keep this on for like 5 to 10 seconds each so that you can understand. For any doubts or queries, feel free to contact us. EDFA versus noise figure. So this is a three-way graph. As you can see over here, you have three different axes. Here on the left side, or left y-axis, what you have is your noise figure. On the x-axis, bottom over here, you have your input power in decibels per meter, and again on the right y-axis, you have your gains in decibel. SNR degradation. SNR stands for signal to noise ratio. So as your amplifier numbers in length, amplifiers increase over length, right? Signal power or signal to noise ratio kind of increases. Then you have your amplifier. The amplifier reduces that SNR noise, and so on and so forth. Passive gain control, pretty easy to understand over this. Wavelength conversion. So this is where a quite important device, Mach-Zehnder interferometer comes into play. This is also known as MZI. As you can see from this diagram, we have multiple wavelengths coming in, which are then either coupled and decoupled as per your requirement of output frequency that you need, and then either they are given out, or you can even take an input signal over here. So this is not a unidirectional device as you might have usually thought, that you give input from the left end and you get the output from the right end. You can give input from the left and right end both and get an output at the left and right end both at the same time. Or you can have 3 inputs and 1 output, or 1 input and 3 outputs, and or the various combination of it. Right? This basically works on the principle of dividing obtaining the output signal on the division of frequencies. Internally, yes, it does use a bit of these various fiber amplifiers that we saw about. One of the prominent ones that we are using over here is the EDFA. But yeah, these various modules or these various amplifiers are used to obtain this Mach-Zehnder interferometer. And that brings us to the end of this unit.